Fools!
As we see, Gandalf has begun a dangerous plunge towards the Balrog. The purpose of our project is to control Gandalf's fall through the automation of magical wizard thrust. These are the two equations we use to model the velocity of a falling object. Since the control volume is drawn around the object, the two summation terms on the right side of equation 1 represent the change in the air's momentum as it passes through the control volume, which is essentially 0. Equation 2 describes the sum of external forces on the control volume. Here we've got the buoyant force, the drag force, the gravitational force, and thrust. Combining equations 1 and 2 gives the accumulation of momentum equal to the sum of the forces. We coded this into Python and solved for the velocity of each new time step using ODE int.
These three plots illustrate Gandalf's thrust, velocity, and position over time. On each plot, you'll see a red line and a green line. The red line represents a free fall without thrust, whereas the green line represents a doublet test. As you may notice in the second plot, our model incorporates simulated noise for the velocity. This is an FOPDT representation of Gandalf's velocity during the doublet test. The black line is simulated data, the blue line uses preliminary FOPDT parameters that a Python optimizer found, and the red line uses re-optimized FOPDT parameters. Through IMC correlations, we converted these FOPDT parameters into initial PID tuning parameters.
We'd now like to demonstrate the performance of our controller. You will see one main graph depicting the position of 3 falling objects, with an insert graph depicting Gandalf's thrust as the controller response. Here, the Balrog has begun falling, and now the sword, and now Gandalf has begun falling. Here he has passed the sword, but it was going too fast to grab it. Once again, he has passed the sword, but was moving too quickly to grab it. And here at about 132 seconds, he was able to grab the sword, and now he has intercepted the Balrog at around 153 seconds. This next animation simulates the same fall, but this time depicting the velocity of the 3 falling objects. Gandalf falls last and most rapidly, especially when his positive magical thrust is initiated. As you can see, the controller changes the thrust to help Gandalf meet his objectives. For example, when Gandalf passes the sword, the controller activates reverse thrust to slow him down. Once Gandalf intercepts the Balrog, both his and the sword's velocity match the Balrog's.
The controller successfully completed both phase objectives, catching the sword and then catching the Balrog. The overshoot ratio for Gandalf's pursuit of the sword was about 1.0, which is typically high for an overshoot ratio, but acceptable for this system because Gandalf still does not yet meet the Balrog's position with this initial overshoot. Now let's see how Gandalf does with his new controller.
We successfully implemented a PID controller for the interception of one falling object by another falling object. Our controller included a double set point of position and velocity, since these needed to coincide for a valid interception to occur. This double set point made tuning the PID parameters more challenging. Future studies could explore optimizing PID parameters based on time-sensitive constraints, in addition to the usual criteria of overshoot ratio, decay ratio, etc.